All right, this is what we have to start with.
So at the end of last class, I asked people why this would be a good choice for our string. Has anyone had a chance to think about why this is a good choice? So to refresh you, the language is AB to the N, A to the K, such that N is greater than K and K is greater than or equal to 0. So we have 0 or more A's at the end of the string, and then 1 or more AB's preceding that. So if we have AB to the M plus 1, A to the M, we still have one more AB than we had A, which is good. But what's the main reason that this is good?
We can't loop on A.
Yeah, we want the XY portion of this getting to the loop and finding that loop, the loop to come from the AB section of the string. Because remember, there are only M states. So if we do M plus 1 ABs, then we know we've reached some loop by about the halfway point in our ABs. So X and Y must be part of this AB to the M plus 1. And we will find this a lot in these kinds of proofs, that we end up needing to proceed by cases. Did we cover proof by cases in discrete?
Maybe.
So let's try to refresh you. So it would be something like, if I wanted to show some property and you could split it into, you knew there was something mod 3, then you could proceed by proof if that mod 3 is 0, then case 1. If that mod 3 is 1, then case 2. If that mod 3 is 2, then case 3. And you start with those assumptions and you work those assumptions through in a proof. You can find that it is true when mod 3 equals 0 and mod 3 equals 1 and mod 3 equals 2, or you find that it's not true for all of those. Then you can build a proof in the general by combining those cases, saying mod 3 can only take 3 values, 0, 1, or 2. So we basically need to figure out, okay, what can X and Y look like when they must come from AB to the M plus 1? Because there must be no way to construct this DFA with M states such that this is true. So we now need to break this down into cases for what this X and Y could look like. And if the DFA cannot be constructed from any of those cases, then this language is not regular. So this is an example of one that needs to be split into cases, because we can't make any sweeping generalizations about X and Y, like Y is all A's, like we did in the past. We can't say that here. What is one thing that Y could be? So we know that this looks like, let's make something that's long enough to be able to visualize the general case, but I want to pick a specific example just to be able to visualize. Let's say that M here is 2. So the string we'd be working with is A, B, A, B, A, B, A, A. We have 3 repetitions since M was 2, right? So 3 repetitions of AB followed by 2 repetitions of A at the end. So this is for 3, this is for, sorry, M is 2. So we know that by here, we need to have found the loop, which is going to make this pretty interesting. If we had a case of 3, just because I want to draw it out, we have A, B, A, B, A, B, A, B, A, and we would know that the loop has to come within here. So kind of generalizing this thought process onto 2, 3, M, what would the cases look like? What could we break this down into and have Y looking like? We'll start with something as easy as possible. In a case for 3, like let's say X is our AB and Y is our A. So Y can still be all A's. Right? You can imagine that there's getting to a loop, parse an A, parse a B, and then you loop back to itself on an A. Then you could do that an arbitrary number of times and still have to be able to produce something that's in the language. So your counter to this idea is you would basically say, let I, this number of times that we're going to repeat this loop, be 2. If that's the case, and Y is an A, then you end up with 2 A's in a row in this section, which is not allowed. So if Y is A, you can also choose I equals 0. I didn't want to model this as well. This says basically that you're not going to go through the loop. So if this is the loop, then we can choose to iterate it 0 times. If we choose to iterate it 0 times, then we get 2 B's in a row, the B preceding it and the B after it. Or you get a string that starts with a B if this X is empty. Either one of those is not allowed in this language. So if you do something like this, then you need to show in general that wherever this A could be, that you need to choose an I that makes it really easy to make a sweeping generalization. So there are 2 cases within this case of having a single A of what that could look like. It could either be at the beginning of the string, if you delete the A at the beginning of the string, then this string starts with a B. No string in this language starts with a B. If it's in the middle of the string and you delete that A, then you get 2 B's in a row. Nowhere in this string can there be 2 B's in a row. So because of this, Y cannot just be A. But that's not the only case here. Y could be some other things, and maybe we can make a DFA work if we picked a different Y. So what else could Y be? Could be some kind of BA, sure. So taking this example, Y could be like a BA. So I'm going to choose AB, and then we can continue this process by showing that. So if Y is AB, something like coming from here, this would say that X is nothing and Y is the AB. So the loop happens right like immediately. It circles back to that initial state. If that's the case, again, choose I equals 0. As soon as you delete this AB, you can re-represent this string as AB to the M, A to the M, because you deleted a single AB. Since this construct says N is greater than K, you would now show that N equals K when you did this, which will violate the language. You do not always have to choose the same I. Even though we chose I here and we chose I here the same, you can choose different values of I, just saying in this case, iterate this loop some different number of times and you produce a string that is not in the language. That's perfectly fine. Do not have to stick with the same I. For BA, it would be a very similar argument as for AB. You would say you're taking the second part of one AB, you're taking the first part of another. So you would end up with AB to the M, A to the M. This cannot dive into these A's because this is AB to the M plus 1. So unless you're doing a deletion that is at least half of the string, half of the number of ABs here, you're not going to be getting into these A's. You probably have to include that as part of your argument to be truly correct. So you'll continue this line of thinking for any reasonable choice of Y, or be able to map. This is where you would want to use something like induction inside of your own proof. I'm not going to do anything that insane to you this quarter, but like something like ABA. You're doing, if you chose A or I equals 0, then you'd be removing an A and you're removing an AB. So you can kind of combine your reasoning from the last couple of steps to construct a proof for any bigger thing, any bigger chunk of Y. So you just kind of combine that logic and say, this generalizes. But if you want it to be mathematical about that, you would need some kind of inductive proof to prove that that generalizes. But again, for the scope of this class, an intuitive proof of that kind is going to be okay. The only part that I'm really interested in you being formal about is the actual proof of this. I want you to follow the exact proof type for any pumping lemma that we do. So these are the most frequent ways to solve a pumping lemma problem. We've seen a few different cases where you just pick a single string in the language of a particular type and the proof kind of works out as you pick something that is easy to prove. Sometimes you will need to break it down into cases. There will be some homework problems that you will work on in this that will require you to break it down into cases and to identify what those cases are and then be able to solve each of those cases. It should be a little bit more apparent than this one. I wanted to choose one that was fairly difficult to break into cases to just show you what that could look like. But I anticipate hopefully seeing a lot more office hours visits during pumping lemma homework because it's not easy. And 3 or 4 examples of this isn't going to be enough to really get that intuitive idea. I understand that I do want to cover a bit more content and move forward, and I kind of want to work with you individually, especially in a topic like this, because how people understand something like this is vastly different from person to person. And I just find that it's easier to work with people individually, where you can walk me through, here's what I have so far, here's my thought process, where am I going wrong? Or I don't know at all how to start this. I don't know how to proceed from here. What can I do? How can I think about this? And I can learn from how you learn and try to tackle the problem from that perspective to help you in that regard. So I find that that is much more effective than just trying to say, here are the 10 ways you can think about this problem. One of them will work for you. So does that seem reasonable? Do we all have availability to meet during office hours or the ability and willingness to come in and see me if you get stuck? Saw some like, looks, we'll go with that. The last thing that I really want to cover is some common pitfalls in these proofs, because I find that when people do go about trying to prove anything, that there are some frequent mistakes, especially in pumping lemma proofs. So the first one is trying to use the pumping lemma to show that a language is regular. This will never work. The pumping lemma is basically it's a proof by contradiction that says, assume the language is regular. If you're trying to prove something, you can't start by assuming that it's true. If you want to prove something is false, you can start by assuming that it's true and deriving a contradiction. But starting with assume this language is regular and then proceeding to prove that it's regular is kind of hopeless. Assume that it's regular, therefore it's regular. You're done. And it doesn't show anything. Any assumption you can make can be proven starting with that assumption. So the one that I most frequently see is no string in the language can ever be pumped out. Doesn't work. That's not something that can be done to prove that a language is regular. So can only use it to prove the language is not regular. If your W, your string in the language, is not actually in the language, that can break your proof. So make sure that you're starting with a W that is in the language. Here's an example where that might show up. Our language is A to the N, where N is a prime number. So some number of A's in a row, that is a prime number. So here we go. Given M, let W equals A to the M. Why can't you start with this?
Can be a non-prime number.
Yes. There may be a non-prime number of states in the DFA to recognize prime numbers. If that is the case, then we can't choose this string A to the M because it won't be prime. It won't be in the language. It's not going to show anything. So it can be kind of hidden like this, where it's not blatantly obvious that your choice is not in the language. You actually have to think a little bit deeper and say, is this guaranteed to be in the language? So if you were to continue this, you would want to use some variable A to the M such that it's, or like, I guess you would need to use something else, A to the, choose something, doesn't matter, such that that is greater than M and that is prime. And then you need to carry that assumption through the rest of your proof. So every assumption that you make needs to adhere to the necessary rules. Last is the assumptions about the decomposition of the part of the string that's before the loop, at the loop, and after the loop. All right, same example as above. L is A to the N, such that M is a prime number. Given M, let our string W be A to the K such that K is odd. Subtracting an odd number of A's from a prime number means that XZ has an even number of A's and cannot be prime. Problems with this?
Two prime.
2 is prime, so that would be kind of an interesting possible counter example to this. But even so, there are additional issues here. That's a good point. So the big one is an assumption like K is odd. Why does that make sense?
It's not given that K is odd.
Yeah, we don't know that for sure. So you're trying to say, given M, let W equal A to the, this is something that's kind of variable. It's not based on a particular assumption. When we say let W equal A to the M, such that M is the number of states in the DFA, and then you go prove something sweeping in that sense, that's great, because any counter example to that would be a particular instantiation of M. It says something like, let M equal 21. There are 21 states to this DFA. Then you could go through and show, here is the construction of that DFA that allows for all of this to actually be true. When you say something like K is odd, it's a sweeping generalization that you can't really make here. Not all odd numbers are prime, so this just doesn't make sense. Like you choose 9. Now we have a string that's not in the language. Questions about common pitfalls in these kinds of proofs? I may circle back and find some more in people's homeworks that I want to talk about in class. But I feel like this is a good start. How do people feel about the pumping lemma? Yeah, somewhere in there. That's probably about what I would expect. I think people need, this is something that you just need to go do and try and beat your head against for a little bit and see if a eureka moment happens to you and you successfully complete some, or if you get stuck, where you get stuck so that you can ask a more specific question about it. So I'm going to reveal this week's assignment sometime, probably tomorrow. And that will include some of these pumping lemma problems. My recommendation is, especially for this assignment, because it's bigger than either of the first two, at least in terms of the number of questions, that get started early, get stuck early, and come see me early, because there's going to be a lot of iteration with this assignment if you end up having some difficulties with this. And I expect in a general college population, I expect 90+% of people to have some kind of issue as they go do this. It's not easy. I don't expect you to be able to complete this without talking to me, working through it. So start early, get stuck early, come see me early. I'd love to see you. I'd love to work to learn how you learn and to help you make this make more sense to you through interfacing with this on your level. It's like, where are you? What do you think? How do you think? I want to learn how you learn. Last questions before we kind of move to a new topic. I know this feels kind of brief, but again, class part 2 is really just office hours. All right, we will circle back to this. As I mentioned to a couple people in class, I have some more practice problems for this that I like to save kind of for the right before the exam part, where we circle back. It's been a little while since we've talked about this, since you had a homework for this ahead of the next exam. This becomes good practice right ahead of that next exam. So we'll come back to it then. But we are going to start talking about a new class of languages. So this is basically everything we've ever wanted to do or will need to do with regular languages, which was this first class of languages that we talked about. We found that it was equivalent to basically any kind of text-based search that we could do, anything that requires no storage or memory. As soon as you need memory, then we need a new class of language. So we're going to start talking about context-free languages, which will allow us a particular kind of memory and an infinite amount of a particular kind of memory that allow us to solve and represent more complex languages. So you can imagine typing in a Control F, some query using a regular expression that says something like highlight numbers that are this many digits or fewer, but you couldn't say arbitrary numbers because you'd have to place a length on that number. You could say numbers that are 100 digits or less, and my counterexample to that would be a 101 digit number that your regex wouldn't find. So how do we handle languages like that? What kinds of structure, how can we augment what we have learned and what we know to find a way to handle these more complicated languages? So why do we care to show that a language isn't regular? Why do we care about languages that aren't regular? The actual application to computer science for this is that, of course, there are programming constructs that require logic that we can't use a regular language for. For instance, we showed that this language, A to the N, B to the N, is not a regular language. What was the reasoning behind A to the N, B to the N not being regular?
You can't sure that they're both the same number of characters.
Yeah, once we read the number of A's, we need to map that number of B's to it. If we read 100 A's, we need to know that there are 100 B's to follow. And we could construct a DFA for an arbitrary upper bound of this, A to the N, B to the N, such that N is less than or equal to 100. Great, that's regular. But as soon as we don't place a bound on n and say n can be arbitrarily large, then our DFA becomes arbitrarily large. We end up with an infinite DFA, which in our modern machines with a finite amount of memory, we cannot create a structure that requires an infinite amount of memory. We just can't do it. Now imagine replacing all A's with open curly braces and all B's with closed curly braces. And you start to see how this language actually represents programmatic structures. So for instance, everyone here is used to thinking about the world in Java. So when you start a class or a method or an if statement or a loop, all of those require curly braces. You can have an arbitrary number of constructs inside of constructs. There's no limit to the number of constructs within constructs that you can have. So if we tried to map A to the n, B to the n with open curly braces and closed curly braces, which is basically what this is, it's a subset of this language that says all of these constructs have to be inside each other, then we end up with the ability to represent this structure. And since it can be arbitrarily sized, we can't have some finite automata unless you want to place some restriction on a programming language that says, all right, you can't have more than 100 structures inside of each other, which you probably shouldn't anyway, but it's not a restriction that we want to replace on our programmers. We'd rather relax that restriction. So now we have a language that we can map to control structures. So if we want to be able to reason about it, we need to be able to construct a more complicated grammar than a regular grammar and a more complicated state machine than a finite state machine. So there are many features that are modeled by such languages. A context-free language can represent this structure. So let's dive into exactly what this class of language looks like, because it is much more applicable to programming language construction and the construction of compilers that need to be able to parse a particular programming language. What restrictions did we place on regular grammars? What was a regular grammar? There were some rules.
Be either left or right linear.
Left or right linear, which meant what?
Non-determinate, whatever left or
Non-terminal?
yeah, non-terminal needs to be on either the right side for everything or the left side for everything.
Yeah, we have an arbitrary number of terminals followed by exactly one non-terminal if it's right linear, or exactly one non-terminal followed by an arbitrary number of terminals if it's left linear. So, context-free, larger class of languages. This tells us that every regular language is also context-free. What you're about to learn with regards to rules will be able to represent every regular language. But it's a bit more complicated. So if you can represent it using our regular language structures, it is much more efficient to do so. But there are many, in fact, infinite context-free languages that are not regular. Because of this, we are going to relax the restriction placed on a regular grammar that the non-terminal can only appear on the right or left side of the production. Now we can have non-terminals in the middle. Let's give you an example. Here is a context-free grammar. Go ahead and analyze it and try to answer some of these questions. What are some possible strings that are produced by this grammar? Draw out some examples. What do we get? Any examples? Yeah?
Like ABBA.
ABBA. How do we derive ABBA? What sequence of productions do we go through to derive that?
Just in order from top to bottom.
So if we go A, capital S, A, we then have, we apply the second production here. So we're gonna have the A and an A at the end. Then we just have a B and a B and a capital S in between. Then the capital S becomes the empty string. So we get ABBA. Great. What's another example?
ABBA.
ABBA. So you said ABB.
No, ABBA. BB.
ABABBA.
BA.
BA. That one?
Yeah.
I don't think that one's possible. Unless I made a mistake.
This and that. There it is. We need to say it again.
Yeah.
A, B, A, B, B, A, B, A.
Yeah, ABA. This one's possible. Cool. I would derive it, but that's a couple more steps. But you can see kind of how how does this work? Well, maybe I'll ask this question first before we go into exactly why. So what language does it represent? If you had to describe this in English, what would that description be? Because what I was about to say would have spoiled that.
Even palindrome or whatever. a baby
Yeah, palindromes. So palindromes that don't have a middle character, kind of that subset of palindromes that we saw before. So we know there have to be an even number of A's because this is the only production that derives A's, and you can't derive a single A. You can only derive two A's at a time. Same with here, you can only derive two B's at a time. But you're always inserting directly in the middle. So of the substring that we are doing right now, we're placing an A at the beginning and the A at the end, and then recursing into the middle and saying, regardless, we're either gonna put an A on the left and an A on the right. So this becomes, the very first thing we did was create these two A's, then these two B's, then these two A's, then these two B's. And that's kind of how that came to be. So now we can see which production we applied for this. If we numbered them 1, 2, and 3, you can see that the first thing we do is, we're gonna kind of do this from bottom to top. We applied 1, 2, 1, 2, and then 3 to terminate the thing. And that becomes a lot easier way of seeing it than actually deriving and writing it out, that you kind of have a way of saying, for where we are right now, pick a rule, we get something at the beginning and end. All right, recursing now into the middle, we'll get something at the beginning and the end. Recursing into the middle, something at the beginning and end, until we hit number 3, which stops, production 3 stops the whole thing. Cool. So we get a string followed by the same string in reverse. A subset of palindromes. So this was the string ABAB, W, followed by WR. Which is another language that we showed was not regular in the last set of slides. So, wow, that was easy. As soon as we relaxed that restriction on placing the non-terminal at the beginning or the end, a pretty simple grammar can represent a language that we could not find a finite size DFA form. We could not write a regular expression form. That's kind of interesting. So why does that restriction lead us to being able to do this? How does this create now kind of an infinite memory, in a sense? Any thoughts on how that kind of changes that restriction? So like with a regular grammar, we had to parse only from left to right or from right to left. So if we needed to do any storage along the way, like how many of these things were we doing, there was no way to do it. There was no way to keep track of that. But something like this says we can now meet in the middle. We can move from the left side and the right side at the same time until we decide to terminate in the middle. Which says that we now have a way of mapping, regardless of the length of these arrows, we can kind of pair places in each of these strings as we move toward the middle. Since these can be arbitrarily long, we can now pair and represent things arbitrarily. So that's one way to think about how relaxing this restriction actually helps us to be able to model some kinds of infinite languages that we couldn't before. So, thinking about a regular grammar, could we produce this language? The answer is no. We know it because we showed that it wasn't in the last set of slides, but why? Why would we have trouble parsing this from left to right or from right to left? And the same idea. We don't know how long it's going to be, and we would need to know how long it's going to be if we were going to be doing this from left to right. We would need to know when W stops and we start on WR. With this, we don't need to. Whatever's on the left is part of W, whatever's on the right is part of WR. We meet in the middle, whenever we terminate, that's where W stops and WR begins. We have a way of figuring that out in this grammar that we never would have been able to figure out in a regular grammar. You have to guess. And it would be possible if we placed an upper bound on the restriction. All W that are less than or equal to 5 characters. Great, now you can kind of check and see, all right, if W is length 1, do we end in a final state? If W is length 2, do we end in a final state? If W is length 3, do we end in a final state? You could construct that DFA. All right, given that relaxed restriction, let's produce a grammar for the language A to the N, B to the M, such that N is not equal to M. A little bit more challenging. Significantly more challenging. I think you have an answer for this. You might not. Try to think of a counterexample. This one's a little bit tricky. In fact, I would argue this is probably the trickiest grammar we've come up with in the class so far. Anyone think they have an answer yet?
I have like an idea for an answer.
Yeah, because the next question I was gonna ask, it didn't look like anyone did, but what are you finding as you start doing this? What process are you using? How are you thinking about the problem? Yeah,
So I start with the starting variable is the two non-terminals, which determines the path of do we want more A's or more B's.
okay,
And then there's gonna be a production that allows for A's and one less B or at most one less B, and then we'll go back to the set of A's or vice versa, depending on which non-terminal is chosen.
okay. That's an interesting path. I think that might work. So we need some way to make sure that we're not generating the same number. But we do still need a production that can produce an arbitrary number of either. We can't make an assumption about the number. It could be that there are 10 billion A's and 10 billion and 1 B's, or 10 billion A's and 1 B. Either of those would be in the language as long as all of the A's come before all of the B's. So take a couple more minutes and see if you can take that idea and run with it. How do you create those productions to kind of put you on different paths? Think of them kind of like an if else. If there are more A's than B's, what is the path through this grammar that you need to take? If there are more B's than A's, what is the path that you need to take through this grammar? Decision time. Do we want to see an answer for this today, or do we want to sit on it and see it at the start of the next class? Any opinions?
Sit on it.
Sit on it for the day?
Time to think about it.
Yeah. Yeah. I tend to occasionally rush things a little bit in these classes, and I do like the idea of, you're giving it your best shot and seeing what you come up with, where you get stuck, because that helps you figure out what about these kinds of problems is difficult. So let's do that, and we will come back to this first thing tomorrow and talk about how do we actually solve these kinds of problems? What do you think through to generate this kind of solution? And given a solution, why does that work? And how do we break it down into its logical components? Okay, I'll see you tomorrow for that. I have office hours for the next hour, if anyone has any questions about the homework. Oh, one other thing, sorry, recording, goodbye.